Thank you all for being here. Let me start off by giving you an outline of what's coming up. Can you hear me in the back? Is that okay? Thanks. Right, this is a very large, broad topic. My hope is to give you a glimpse of some parts of it, but it's probably not going to be complete, unfortunately. I'm going to try to give you more context in like homework problems and so forth, but for the most part, our lectures will split up very nicely into 4 topics. So today, in this short talk, I'd like to tell you about definitions and some constructions and a little bit of motivation. Tomorrow and the day after will be somewhat longer talks, and we'll talk about existence questions and uniqueness questions. So existence will be something like, if you fix for me a homology class inside of a 4-manifold, what sort of surface embedded surface can I represent that homology class with? Or it can be, let me fix some boundary condition, like a given knot. What can I say about the types of surfaces bounded by that knot? So we'll talk more about questions like that. Uniqueness essentially will be uniqueness up to isotopy. And then on Friday, we'll come back and have another short talk. And there, well, there'll be a buffer for depending on how much I'm over time, and we'll see how this goes. But hopefully, I'll talk about other equivalence relations. By that, I mean this will be primarily about the equivalence relation of isotopy, but there's all sorts of other equivalence relations you can think of. You could think about concordance, you could think about stabilization, various different flavors of stabilization. So here I wanted to talk about those. If this doesn't happen, that's also not that bad, but that's the plan. It's the first week of a long program. So my plan is to keep things very general. So especially those of you who work in surfaces in 4-manifolds, you will see most of what I talk about will be familiar to you. My apologies for that. But my plan really is to talk to people who are really seeing this for essentially the first time. So my apologies if that does not apply to you. In particular, this does mean that you have to keep me honest. So if I start going really fast, if I start assuming lots of things, please do tell me. Here's one way that you can do this. If I'm going very fast or going very slow, if I'm saying a lot of things that you don't understand, please tell me. You're definitely welcome to tell me in person or in the tutorial session or whatever. There's also an anonymous form. So there's tinyurl.com, and then my name / feedback, -feedback. There are also some homework problems. These can be found here. Again, my name, and then problems. Christine mentioned that maybe the link will be posted on the conference website as well. And then finally, there are the tutorial sessions. I believe my room is 15. It also has our names on it, so it'll be easy to find. So in the tutorials, in that room, I hope you'll feel free to talk to one another, especially those of you who have worked on these topics before. Maybe you can help folks who are seeing it for the first time. That would be really great. Personally, I plan to be there starting 4:30. So if you would like to talk to me, you will find me in that room at 4:30. Okay? All right, so those are some logistics. Any questions on logistics? Okay, great, let's get started. All All right, so I want to start off with some definitions. As you see today will be relatively overviewy. We won't talk about theorems exactly today. But let's make sure that we're talking about the same basic objects. So let's start off with a starter definition. So a smooth knotted surface for me, or sometimes a smooth surface knot, is a smooth embedding I'm going to call it K of some surface into some, in general, some four manifold, but for now let me say S4, where this is a closed surface. So closed, I mean compact, no boundary. If sigma is S2, this is called a 2-knot. So these are sort of the very first surfaces in four manifolds that people usually encounter. I'll give you some examples in a second, but let me start off by talking about this a little bit more. There are some obvious generalizations. So you can see there's no reason to stick to S4. It's just when we talk about two knots, usually, classical knot theory considers S1s and S3s. And so high dimensional, or the next higher dimensional knot theory considers surfaces in S4. But there's no reason to limit ourselves that way. So of course, we can consider more general surfaces, like in some arbitrary M4 instead of S4. And then we can also consider surfaces with boundary. And here I want to give you another definition of something we'll see very often. So bad placement. So let me do this here. So this definition is going to bring together both surfaces in four manifolds and knots inside of S3. Given a knot in S3, given a 1 knot, little k from S1 to S3, we say it is sliced, smoothly sliced. If we have the following, so I have, if there exists a smooth embedding, delta of D2 sitting inside of B4, such that on the boundary, I have my original knot, little k. Okay. There's a comment about this earlier. For me, disks are things that get embedded, and balls are things where places where they get embedded. That's why I make that distinction. Doesn't super matter. And so here you can see this, of course, is some interesting surface. This is not a very interesting surface. It's just a disk. But what's interesting about this embedding is that it has this given knot on its boundary. Okay. And then the final comment I wanted to make here is that often we will not really make a difference, so we'll conflate a knot or a surface or whatever. So we'll conflate the embedding and its image. So by which I mean, so far I've tried to be very careful and say that surface knots, knotted surfaces, one knots, they're all embedding, so they're maps. But most of the time we just consider their images. Or if you're trying to prove something or write down definitions, you should be careful, but we will not be that careful. Okay. Does the definition make sense? I'm going to give you some examples now, but definitions seem reasonable. Yes? So when I'm considering 2 knots or S4 or 1 knots, I will want them to be embedded, oriented most of the time, but it's not really necessary. So especially when we talk about these uniqueness questions, mostly the uniqueness questions, not so much the existence questions, we'll also consider these unoriented or non-orientable settings. But right now it's just pretty general, and I'll try to specify. Yes? That's a great question. So I'm considering the standard smooth structure on S4, which you could think of it as, I guess, submanifold of R5, if you would like. Whether or not S4 has multiple smooth structures is an open question. There are ways of approaching that question using surfaces in 4 manifolds. That will be part of the motivation at the end of the talk. But I'm considering the standard one. Other questions? All right, so far, these are just some abstract definitions. Those are not so much fun to work with. But I'd like to give you a couple of methods for how we, 1, visualize, and 2, construct such surfaces. Okay? Of course, we can work in very general 4 manifolds. That will come up more in lectures 2 and 3. Today, I'm going to primarily stick to B4 and S4 just because that's hard enough. So let's do that. Okay. How come that moved? Okay. This seems fine. I don't know how I achieved it, but I'll take it. Okay, so how to construct these things. As I mentioned, we'll see a couple more of these in later lectures, but for today I want you to see 2. Here's the first method. These will be movies, or some people call them motion pictures, but let's call them movies. And I want to explain this using the notion of a slice knot or a slice disk. In order to do this, well, we're trying to visualize surfaces right now in B4. So in particular, you need to know how to visualize B4. Before you can put something in it, you need to know what your ambient space is. So let's consider the following cartoon picture. I'm going to think about B4 as S3 cross the interval. And then I'm going to collapse this final, like all of the S3 at that final 1 coordinate, I'm going to collapse it down to a point. So I'm just thinking of B4 as the cone of S3. Nothing especially interesting. So how should I think about B4? Well, could think about it in the following way. This is a kind of cartoon picture Which one is 1? No, this one. Okay. So here's a sort of cartoon picture for this. This looks like R3, but it's actually R4. That's my cartoon. So I'm thinking of this flat plane as 3 coordinates. It's just I've collapsed one of them. In the vertical direction is what we usually call time. So it's going up. That time will be that interval coordinate over here. So in particular, any knot that I'm thinking of slicing will live in this R3 as a subset of S3. And I'm going to build a disk that is allowed to leak into this 4th dimension. This is very confusing when you see it the first time. So let's try to do it a bit carefully. So I'm going to draw here a knot. I'll draw a bigger picture in a second, I promise. But the knot will live entirely in this flat S3 3-dimensional bottom. And now, if I were trying to show you that this knot is unknotted in S3, I would have to find you a disk in the flat plane. This knot is not unknotted. I'm only claiming that this is slice. So I'm going to build for you a disk that is allowed to live in this upper half space. Okay, so this has hopefully convinced you that the unknot is slice. And I'm going to now try to convince you that this knot is in fact also slice, even though it is not unknotted. Here's how this will go. So I said that there will be a movie. I'm going to build you a disk that leaks into this 4th dimension. I'm going to chop up that disk into these horizontal segments. Each of those horizontal, don't want to say slice, okay. Chunk. Each of these horizontal things is a copy of 3-dimensional space. And when I play all of those together, I get a movie. Okay? Here's what I mean by that. I'm going to draw you a disk that kind of looks like this, schematically. So here will be my knot, now drawn as being a circle. And the disk will look like this. And I'm going to look at these horizontal slices. And as my time changes, at time equal to 0, I will see my original knot. Slightly higher in time, I'll still see a circle. At some point, as I pass through the saddle singularity, I'll see something that looks like the number 8. Beyond that, I'll see 2 different circles. And these circles will shrink down to points. And then they'll disappear. Now I'm going to draw you a disk like that for this knot, which will be much harder for me to draw here properly. But what I'm going to draw is draw each of these pieces separately so that in your mind you can play the movie as you travel forwards in time. Okay? So here there will also be a disk. I just don't want to draw it because it will not be accurate. But let me show you the actual stills from this movie. First, you're going to get this knot at time equal to 0. This knot is called the stevedore knot. This is a situation where orientations are important. I'm going to not think about it too much, but it will be relevant that no matter how I orient this knot, this strand and this strand will point in opposite directions. Don't think about that too much if you'd rather not. I'll do a modification here. Roughly, the modification I'll do there is these 2 strands will go to this picture. And so in fact, what will happen as I go from this picture to this picture is a saddle singularity. So that's what's happening roughly over here. What that means in my movie is that at some point I'll have this point of intersection that I've grossly exaggerated. But these two pieces of the knot will come close to each other. At some point they'll touch, and then they'll resolve in the other direction. So it'll look like this. So going from this picture to that picture, I've done this modification. And this time is precisely the one where I have these two circles touching at a single point. Here I had a single circle. Here you can convince yourself that I have two circles touching at a single point. Now I have two disjoint circles. Now I can do an isotopy to bring these fingers down. So I get this. And then I could shrink those down to points. And then I'll have the empty set. Okay? And so I could label these. I'm sorry for not sticking with my color coding. Is that a light that should be on? Maybe not. No? It doesn't matter. This can be So this is what I mean when I say a movie describing a surface living inside of B4. Okay. Is it bright enough? Can people see things? Maybe I could change my choice of colors. All right. Thank you for trying. Okay. Is the board visible? Sufficiently visible. Thank you. Thank you. Question? Why do I do this? So right now, I'm not saying you have to get this. I'm saying that this is a choice you can make. So, because you have told me, here's a knot, is it slice? And all I have to do is build you a surface, a disk, sorry, a smoothly embedded disk. And I'm giving you a way to do that. And so what I'm trying to convince you is that this is an acceptable strategy. There is something a bit more complicated. It turns out that any smooth surface inside of S4, B4, whatever, can be slightly isotoped, so that if you consider the height function given by the radius, and if you think of S4 as essentially being S3 cross interval with 2 points collapsed, just as we did here. Given any surface inside of S4, you can perturb it so that with respect to that height function, your surface is Morse, which means that all of your critical points will be of certain types, and they'll be precisely minima, which look like this. I guess those are maxima here, sorry. Minima or maxima, depending on your perspective, and saddles. That's exactly right. So if you know about Morse theory, ambient Morse theory, and things like this, this is actually pretty general. I just had maxima here. You could have had minima. That's fine. And that essentially describes all possible slice disks. If you don't know about these things, you should just think about this as a construction. And that's all I needed to show you that that knot is slice. Did that answer your question? JB had a question.
I
I think that's completely fine. You could have done B3 cross interval, and that would have been just fine. I think in terms of these movies, it would be equivalent. I don't know why I wrote it this way. It's just at some point I saw it this way and it stuck, but there's no reason not to do it your way. Other questions? That's a great question. I will talk about non-smooth surfaces in a few minutes. It's more complicated, but it is possible. More on that later. There's another question. Yes? This is a ribbon knot. OK, you've come prepared from knowing other terminology. So it turns out that this disk that I've described is something called a ribbon disk. A ribbon disk, by definition, is a disk which looks like this, which just has, OK, in the picture that I've drawn, it just has maxima and saddles. But usually you draw it the other way around, so you'd only have minima and saddles. So there are only caps, no cups, and therefore it's a ribbon disk. It's a very interesting question whether, so a knot is called ribbon if it can bound a ribbon disk. It's a very interesting wide open question whether all slice knots are ribbon. Obviously ribbon knots are slice. But since you know the terminology, you can consider the question, is every slice disk a ribbon disk? And that is a much easier question with the answer no. Yes?
Looks like symmetric knots.
You can't. OK? That's the answer. That's a great question. So not every knot is slice. How do you know? We're not so much, I mean, I can say a little bit about that tomorrow, because that's sort of part of existence, or rather non-existence. Here, I mean, I came prepared with this knot, so I knew to do this move. And you could try to do it to any other knot. Sometimes you will fail. And there are obstructions, so not all knots are slice. And so you can always try to do this saddle move, but you will not always succeed. I promise. I'll tell you tomorrow. All right. Anybody else? I promise that not all knots are slice. Maybe I could tell you that the signature of a knot is a slicing obstruction. So for example, the trefoil knots are not sliced. Okay. All right. So let me give you one more method. And again, I promise you'll see other methods later in the course as well. This is sort of a standard method. It's a good one to see. This is called spinning. This one was very pictorial. So I thought for the second one, I tried to give you some equations. So if you're used to some equations, maybe this will help you feel a bit more comfortable. This was some, oh, I should have mentioned, I built you a sliced disk. But if you prefer to have closed surfaces, you could imagine taking two sliced disks and gluing them together on their boundary. OK, so secretly, I've given you a way of building two knots in S4 as well. And I mean, these were disks. Maybe all of you could think about if you didn't care for a disk and all you wanted was a surface, then could you do something similar? In that case, the answer is yes. You can always get some surface bounded by a knot. So OK, so you've already seen secretly a method of building two spheres in S4. But here's a different method for doing the same thing. I promised you equations, so let's have some. So I'm going to consider the upper half space in R3. And so by definition, that will consist of these points inside of R4. And so what I'm doing is I'm thinking about a way of thinking about R4 as copies of the positive half space in R3 spun around something. It's very confusing the first time you see it. Here's the thing that will spin around, just plain old R2. Just all of those inside of R2, inside of R4, sorry. And so what do I mean by spinning? I mean that if you give me an X inside of R3 plus, and you give me a theta that lives between 0 and 2 pi, then I could consider the point x theta, which will be by definition the point x1, x2, x3 cosine theta, x3 sine theta, obviously lying inside of R4. Let's see if that works. Oh, yes, great. No? Okay. That's a scary noise. Is that supposed to sound like that? Okay. Nothing broke so far. So, given a subset of R3 plus, we can define the spin of X as the following. This is going to be the collection of all x thetas for x in x and theta in 0 to 2 pi. And the thing you have to notice is that if you take R3 plus and you spin it, sorry, so spin of R3 plus is equal to R4. Okay? That is too many. There's not even that many equations, but that's too many for me. So you could consider, like, how can I build R2? I could take the positive real line, the positive real ray, and that spin it around the origin, and I get all of R2. And now you could think about R3 by taking that picture that I gave you and taking that cross interval. So I have this half plane, and I spin it all around this axis. That's how you get R3, but you want R4. So now you're going to take your positive real thingy cross R2. Now you're spinning around that origin point cross R2. And this thing you're spinning is an R3 plus. So sometimes that seems very simple, and sometimes that seems very complicated. Not even depending on you, depending on the day. So do you believe that spin of R3 plus is all of R4? Just think about this positive real line, positive real ray thing. And if that makes sense, the formulas are supposed to convince you that I'm not cheating. Okay, so this is a way to build all of R4. So now how do I build an S2 inside of R4? Well, let's consider the following. Here's R2. here's R3 plus, which is everything above here. And now I'm going to show you an arc that I could spin. So we'll call this thing L, or A, sorry. Not that it matters. So that is an arc sitting inside of R3 plus with its 2 feet standing on R2. Now when I take that picture and I spin it around this base R2, I'll get a 2-sphere. Okay? And you should think about, if this was a nice straight circle, you would totally agree with me, because this is like the lines of longitude on a globe. So I could take one of those and just spin it around. Like, I don't know, like in an ice cream scoop, you know, when there's that thing that makes sure all the ice cream goes out. Like, that's the thing, except all the way around. Maybe a melon baller? Is that a thing? Like, how do melon ballers work? I'm not sure. But if this were a straight, round semicircle, you would totally believe that it's an S2 that gets built. And now, because of the magic of dimensions, it's still an S2 that's being built. It's just that every slice is like 3-dimensional instead of 2-dimensional. Okay. And so usually, if I were to draw an arc here, let's call this L, then you'll notice, sorry. So I'm making a knot of myself. Trying to spin things around. All right, great. Okay, so if this is A, then the first thing I should note is that the spin of A is a 2-knot. And then, I mean, you notice that if L is an arc here, then L union A is a 1-knot. Another place where you might care about orientations, but not that important. So make sure it's with the right orientation. I mean, usually called spin A, the spin of this 1-knot. So in particular, the thing that we built, I would call it a spun trefoil, because this picture that I have drawn is of a trefoil. Doesn't matter what it's called. Whatever it's called, the 2-knot will be the spun, that knot. Okay. So spin A is usually called the spun, whatever the name of L union A is. So for example, in this case, this is the spun trefoil. Okay. All right. These are the 2 methods I'll talk about. I want to switch gears a little bit for the rest of this hour, but questions about this? Question? That's a great question. There are obstructions. I will not discuss them, but this is a good question. Maybe it's worth mentioning here that the thing that I have described to you right now, this is called zero twist spinning, and you can do all sorts of generalizations of this. So you can imagine, for example, that as you're spinning, you also do some sort of isotopy, so that by the time you're back, you've returned. But in the meantime, your path was somehow interesting. And so, you know, the 2-knot that you've built, the 2-knot that you've described is not necessarily the same. It turns out that you can very precisely describe the fundamental groups of these 2-knots that you produce in this way. I mean, it depends a little bit on how messy your isotopy is, but basically we have some nice formulas, and there exist 2-knots that have more complicated fundamental groups. But one of the things that y'all will do in the homework, I hope, is to show that the pi1 of the 2 naught that you got from this 0 twist spinning is the same as the pi1 of the complement of this knot, like the trefoil, which is a nice exercise you should do. But that's a great question. Yes? I think maybe the 0 twist spin is ribbon. I think that is right. This is a spoiler for a homework, but I think if you do just the half, you'll see that it's a ribbon disk. And then you've put 2 ribbon disks together, so that's a definition of a ribbon 2 knot. The 1 twist spin is the unknot, and then the other twist spins are not always ribbon. I think that's right. So the 0, I think you're right. That's right. That's a great point. So Jean-Baptiste points out that the 0 twist spin is, I'm pretty sure, a ribbon 2 knot, and not all 2 knots are ribbon. Under a different meaning of ribbon that I don't want to discuss. Other questions? Sorry?
In the movie, do we need to do just one resolution?
In method 1?
Yep.
I mean, in this one, because I chose the example, it turns out that there's just, when you say resolution, you mean the saddle thing. So in this case, there's just one, but that's not always the case. So there exist, so the number of these saddles is something that you might call a fusion number, and there are bounds on the fusion number. So it's not always one. No, that's what I was trying to say. So there exist ribbon disks with arbitrarily large saddle number or fusion number.
Okay. But
or that should be true. I don't know the reference, but that should surely be true.
if you fix them off, you can always just put one saddle on some.
No, even for a given knot, so of course, given a ribbon disk, you can always make it have more by being silly in your construction. So for a fixed knot, you should define the saddle number as some sort of minimum over all ribbon disks. And if your knot isn't ribbon, it's infinity. But even for a given knot, the number of saddles you might need could be very large. And I believe arbitrarily large. Thank you. I'm going to erase the board, but if you have more questions, do ask.
So in the movie, people 1/23 is 3/4. So we are just isotoping it?
That's right. So there was just one thing. So that was the original knot at the beginning. Then that was the figure 8, and that was after the saddle. Should have been closer. But after the saddle, so between 1/2, or really between 1/4 plus epsilon to 1 minus epsilon, everything is an isotopy.
Why not take 1/2 and 3/4?
Sorry?
So why not 1/2 and 3/4 plus 8? We are just isotoping it.
The reason I tried to make it an isotopy is I wanted to make it clear that these shrink down to points. So it kind of depends what you're trying to do. So I was just trying to show you that it shrinks down to points. If you wanted, you could just have shaded in the disks over there, and then your disks are kind of flat instead of nicely flowing with respect to the 4th dimension. But that's, so you could introduce some corners. Corners are scary, so I tried to avoid them. Now I'm going to keep moving. Feel free to ask me questions later. All right, so I promised I would say something about non-smooth surfaces. So let's do that. So far, everything has been smooth, but you don't need that. Smooth surfaces are nice, but there exist other very nice notions of surfaces. So here's one of them that I especially like. So if you have topological embedding, meaning injective map homeomorphism onto its image of a surface inside of a four manifold, this is said to be locally flat. If, let me draw you the picture first. So you have your picture f of sigma. What I want is for every x in sigma, this is a two manifold, of course, and this is a four manifold. So for every point in the domain, I'm going to look at its image, f of x. I'm going to find, I'm living inside of a four manifold. So of course, any point has a neighborhood that looks like R4. So there exists a neighborhood of f of x. Well, of course, I know that this neighborhood is homeomorphic to R4, but I want something of the pair. So I'm going to ask that the pair u comma the intersection with the image admits a homeomorphism to R4, R2. This is if x is in the interior of sigma. If it's in the boundary, there's a different condition, but let's not talk about that. What is this saying? This is saying that if you look in on each individual point of the embedding, it looks like the standard two-dimensional embedding. Okay. Smooth embeddings are locally flat, but not necessarily the other way around. Okay. This might seem very difficult to work with. There is a question about whether it's possible to visualize locally flat surfaces. And the answer is, there's two answers. The first is that, well, everything we did, for example, in the movie pictures, the motion pictures, you could try to do it patch by patch and then glue them together. It's not impossible, but it's also not a lot of fun to do that. But you can draw extremely explicit pictures that way because your local picture is so very nice. But there is one more very important fact. This is a big result of Frank Quinn from the 80s. He said that locally flat submanifolds of any four manifold these admit normal vector bundles. So in particular, if sigma inside of M4 is locally flat, what does it mean to have a normal bundle? It means I have a nice tubular neighborhood. It means that I can always find a neighborhood of this sigma so there exists something like this. This is the total space of a D2 bundle over sigma. And so there is a D2 bundle over sigma whose total space embeds in M4 as a neighborhood of your given surface. What I'm trying to indicate by this is that this is a global answer. So your locally flat surfaces still have nice tubular neighborhoods. And that means that a lot of the things that people like to do for smoothly embedded surfaces, we can in fact do them for locally flat embedded surfaces as well. Why is this not obvious? The difficulty there, well, in the definition, I just gave you something very local. And then all you know is that those local pictures fit together locally. But in order to stitch them together to get something global is non-trivial. And maybe the cheating answer is that this is not true in higher dimensions. So there exist locally flat submanifolds in higher dimensions that certainly don't have normal vector bundles. They also don't have normal microbundles. So they're just very bad.
But I mean, a bundle is always something local. If you have a bundle locally, then you have a bundle globally.
Yes. The global thing is about that total space living as a neighborhood. And embedded. So maybe it's worth think about some not locally flat spaces, like think about the Alexander Horn sphere, if you will. And so, I mean, it is NS2 living inside of R3 in an interesting way. But because your embeddings can be really, really complicated, like bundles don't have necessarily enough space to fit. It's not a very good answer. But this is a highly non-trivial result. And in particular, does not hold in high dimensions. Yes? In codimension 2, you get normal microbundles. Sorry, where? Who? Yes.
I have a silly question. So what if we drop the locally flatness condition? Is it
That's the next thing I was going to write, so let me write that. Oh, no, stop. Don't go. I agree that the embedding of the bundle is non-trivial, but I also don't have an additional compatibility condition. I really just mean this. But I only have 5 minutes, so I kind of want to keep going. So let me ignore you for 5 more minutes while I do this. So let me first address Oza's question. So beware. Not all top embeddings are locally flat. So for example, you could take any interesting knot inside of S3, and then you can cone it. So you could consider the cone of K inside of the cone of S3, which by definition is B4. What you'll get is a picture like this. That's a disk. So that's a disk sitting inside of B4. This is locally flat if and only if K is the unknot. So in some sense, that's an answer to Oza's question about, well, if you had defined slice to mean as the boundary of any disk, then any knot would be topologically sliced. That would be sad. But In fact, what you do instead is you say a knot is topologically sliced if, well, I have my key in S3, and just like before, I'll ask for an extension to an embedded disk, but I'll only want this to be locally flat. Okay, that's something called topological sliceness. And I mentioned earlier that not all smooth embeddings are locally flat, but not the other way around. And one nice way to see this is that this is a fact that was first observed by Kasprowski and Apollout using results of Freedman and Quinn. Donaldson. So used to saying that. There exist knots that are topologically sliced, but not smoothly sliced. For example, the positive Whitehead double of the right-handed trefoil. I'll talk more about this tomorrow. But the point is that this knot is topologically sliced, so in particular there is a locally flat embedded disk. This fact tells you that that disk even has a nice tubular neighborhood, so there's a D2 cross D2 with boundary a tubular neighborhood of your knot. But that disk cannot be even isotoped, Rao boundary, to a smooth embedding, because if that were possible, this would be smoothly sliced, which it is not. Okay? So in particular, this example is supposed to show you that locally flat embeddings are not smooth embeddings. No, still ignoring you. Can't hear anything. Can't hear anything. Everyone's so quiet. That's great. Okay. Let me just say some motivation for studying surfaces in four manifolds. Then I promise I will take all of your questions. As expected, everything took longer than I anticipated. So why do this? Why do we do this? I want to give you 3 reasons, and that will be the end of the talk, so let me give you the 3. It will take me a bit of time. My apologies. So since this is right here, let me just point to this one. First, every knot that is topologically sliced but not smoothly sliced gives rise to an exotic smooth structure on R4. Exotic means it's not diffeomorphic to the standard smooth structure on R4. And in particular, uncountably many such smoothings arise this way. This was not the first of exotic smooth structures on R4, but it's certainly a very nice one. This was first written down by Bob Gompf. He uses, for example, these results of Freedman and Donaldson, And it also uses very centrally a result of Frank Quinn. So potentially understanding these slicing problems of knots and links could tell you something about these. I think I speak for all of us that when I say that exotic smooth structures on R4 are pretty cool. So I don't think I have to convince you about that. So in particular, this could give us a way of understanding those. Oh, no. I can't do both. You might say, well, okay, fine. I don't even care about exotic smooth structures on R4, which is, what? Of course you care. What are you talking about? But in fact, maybe what you really care about are exotic smooth structures on S4. So it turns out that there are ways of going from these slicing questions in more general four manifolds to go from that to questions about exotic smooth structures on S4. There is a problem on that. That is not the problem. The strategy is a problem in your problems list, so maybe you'll find the strategy there. There's another potential strategy to finding exotic smooth structures on S4, which is called Gluck twisting. Here, what do? Well, I start off with a sigma, which is a 2-knot inside of S4. It's a 2-knot in S4. So in particular, it extends to an S2 cross D2 in S4. And what I could do is I could take S4, 4, remove that S2 cross D2, and then glue it back in. In order to do this, I need to tell you how to identify this boundary S1 cross S2 with this boundary S1 cross S2, sorry. And I do this so that when I go along that S1, I rotate that S2 all the way around. So in particular, that means that if I have theta comma x, that goes to theta rotation by theta of x along some chosen axis. This, by definition, is the Gluck twist of S4 along sigma. And it turns out that this is homeomorphic to S4, but not necessarily diffeomorphic. So it's a very interesting open question about whether this could be a method of constructing exotic smooth structures on S4. I won't have the time to write this down. So we have no example where this produces exotic smooth structures on S4. Otherwise, you would have heard about it. But it is possible to use this construction to create some exotic smooth structures. Let me not write those down. There are also other procedures on surfaces in four manifolds which do lead to lots and lots of exotic smooth structures. There's a procedure called knot surgery, which can produce infinitely many exotic smooth structures on the K3 surface. Let me not write any of those either. Let me write my promised third thing instead. This is something in the purely topological category. It's going to be extremely fast because I'm already over time. My apologies for this. Do it in 3 sentences. Shit. There is a very powerful tool in high-dimensional manifold topology called the surgery sequence. The surgery sequence does not work for smooth four manifolds, but it works for topological four manifolds sometimes. Third sentence, the surgery sequence is exact for all topological Four manifolds if and only if all so-called good boundary links are freely topologically sliced. I.e., if L now 2,000 words. There's the Baromean rings. That is the Whitehead double of the Baromean rings. Prove this is topologically sliced. That implies the sequence is not exact. Profit. Thank you for your patience.